All right, so the first part of part C asks us to find the standard deviation of x. Let's go ahead and do that. The standard deviation of x is given by this equation right here, minus the expectation value of x quantity squared. And we found that in part B, this expectation value of x is 0, and the expectation value of x squared is given by this right here. So the standard deviation is simply just the square root of 1 over 2 lambda squared, or 1 over root 2 lambda. So this is the standard deviation. And now we are to graph the probability of density. So that looks like this, lambda e to the minus 2 lambda absolute value of x. So we're going to have to graph this now for the second part of this problem. So let's go ahead and do that. It's symmetric about the y-axis, and it's an exponentially decaying function. So it's going to look something like this. And this maximum right here is at x equals 0, and it's just lambda. Sorry, I know this kind of looks terrible right here. It's fine though. And then Griffiths wants us to basically find the value of psi squared at the expectation value of x plus the standard deviation and the expectation value of x minus the standard deviation. But the expectation value of x is 0, so we just need to find what psi squared of the standard deviation plugged in is and the negative standard deviation plugged in, but you can see that it's going to be the same value due to the symmetry here. So what is this? So this is lambda e to the minus 2 lambda times the standard deviation, and the standard deviation is just 1 over root 2 lambda. So this just equals lambda times e to the minus 2 over root 2. And e to the minus 2 over root 2 is approximately 0.24. So that means that this is 0.24 times lambda. So this is the value of the wave function squared at the positive standard deviation. And it's also the value at the negative standard deviation. So 0.24 of lambda is approximately a quarter of lambda, so it's about right here. 0.24 of lambda. And this value right here is the standard deviation value. And this is essentially just the spread in x, this region right here, because the particle is most likely to be found in this region, since after this region it sort of diminishes and comes close to 0. So the probability of finding the particle outside this region will be fairly small, and Griffiths actually asks us to find this probability. So to find that probability, we just need to find the probability of finding the particle outside of this range right here, or outside of this range. We just need to take the probability from the positive standard deviation all the way to positive infinity, and due to the symmetry, we can just multiply it by 2, and that will give the probability of this region as well, from negative standard deviation to negative infinity. So let's go ahead and do that. So the probability out will be this integral right here from the positive standard deviation to infinity of 2 lambda e to the minus 2 lambda absolute value of x dx. So we just need to find this, and we'll find the probability of finding the particle outside of this region right here, outside of the spread. So this is a rather simple integral. You just get 2 lambda over minus 1 over 2 lambda e to the minus 2 lambda x, evaluated from the standard deviation to infinity, and the two lambdas cancel, and you're just left with negative 1 times e to the minus 2 lambda x as x tends towards infinity, which is just 0, minus e to the lambda minus e to the minus 2 lambda times the standard deviation. And we found this quantity already. It's just 0.24, so this is just going to be equal to 0.24, as the negatives will cancel right here. So this is the probability of finding the particle outside of the spread of the function. So outside of this range right here, that's the probability. So you can see it's fairly small. So yeah, that's the end of the problem.